Hi everyone, this is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about endurance limit problems. In previous session already we have studied. So what do you mean by endurance limit and what is the fatigue failure phenomena, and then what are the loading effects, loading correction factors effects on endurance limit. So based on these effects on endurance limit and based on variable stresses methods, whenever the component is subjected to the combined steady loads, you have to solve some problems. So already we have derived some formulas also in the previous session. So now in this session we will see problem solving on endurance limit. So this problem based on variable stresses. So whenever the component is subjected to combined steady and variable stresses, so need to calculate the diameter of the shaft or the stresses, endurance limit value or mean stresses of the particular component when subjected to reversed axial loads or reversed bending loads. So we have three methods. One is Gerber parabola, another one is Soderberg, and Goodman line method. By using the three methods, how to solve the problems. So already we know the equations of a Soderberg and Goodman line method and Gerber parabola. So by using the derived equations, we need to solve the problems. So how to solve this type of problems, I will see. I will explain in this session. So first problem, a 50 mm diameter shaft. So the diameter of the shaft is given 50 mm. Is made from carbon steel. The material is carbon steel. Having ultimate tensile strength of 630 megapascal. It is subject to a torque which fluctuates between 2000 Newton meter to minus 800 Newton meter. So using Soderberg method, calculate the factor of safety and assume suitable values for any other data needed. So here he has given diameter of the shaft. So already in given data written, and then ultimate tensile strength 630 megapascal sigma u, convert into Newton per mm square. It is subject to a torque which fluctuates between the torque is the given torque T max is equal to 2000 Newton meter. T minimum is minus 800 Newton meter. So it means fluctuates, the torque is minus 800 to 2000 Newton meter. So clearly given in this problem using Soderberg method. So the Soderberg method is useful for ductile materials. Calculate the factor of safety, assume suitable values for any other data required. So suppose calculate factor of safety. If you need sigma y value, so you have to assume sigma e, and what is the relation between sigma u and sigma e. So these values you may assume. So other suitable data. Clear? So first we know that the mean or average torque. So calculate mean or average torque. So average torque is equal to T max plus T minimum by 2. So maximum torque given as 2000. Minimum torque is minus 800. So that the substitute those values and calculate. So 2000 minus 800, 1200. by 2. So 600 Newton meter. Convert into mm. Multiply with 10 cube. So the mean, the torque fluctuates between minus to minimum to maximum. So that you have to calculate mean torque. Similarly, calculate mean or average shear stress. So shear stress formula, the relation between shear stress and torque, already you know, T is equal to 5 by 16 tau into dq. So here given the torque is mean torque. Shear stress we don't know, need to calculate. So that shear stress is equal to 16 T mean by pi d cube. 16 Tm by pi d cube. So the shear stress, shear mean is equal to 16 mean torque 600 into 10 cube by pi d cube. So substitute the values. D is 50 mm given. So after calculation, so you may get 24.4 Newton for mm square. So mean torque and shear stress calculated. Now calculate average average torque or variable torque. So variable torque is T max minus T minimum by 2. So maximum value already you know 2000. Minimum is 800. So divide by 2. So you will get 1400 Newton meter. The 1400 Newton meter convert into Newton mm. So now we have values mean torque and then shear stress value and then variable torque values. So immediately calculate after finding the variable torque, variable shear stress. So by using the torsion equation. So T is equal to T T variable 5 by 16 into tau variable into dq. So variable stress is variable shear stress written like this formula and substitute all values, you will get 57 Newton mm square. So endurance limit for shear loads, you may taken like this, sigma E is equal to 0.55 sigma E. So already we have studied in our earlier sessions the shear load, for shear loading, the loading factor you may assume 0.55 for ductile materials. If given material is ductile material, so that you may be taken 0.55 sigma E, and then the sigma E relation between the sigma E and sigma U, the endurance limit and ultimate stress, ultimate strength. So this for steel material or for ductile material, sigma E is equal to 0.5 times of ultimate strength. So that substitute this relation in this sigma E. So finally you may get 0.275 sigma U. So obtained the shear endurance limit is equal to 0.275 times of ultimate strength. Now assume other stresses and other factors. So in your problem not given the other yield stress. So yield stress value for carbon steel in reversed bending as 510 Newton per mm square. The surface finish factor as 0.87 and size factor is 0.85. Fatigue stress concentration factor is 1. So you may assume these values not given these factors in your problem. So that assume all these factors and then multiply with the endurance limit value. So then you will get the actual endurance limit stress for a particular component whenever the component object is subjected to variable loads. So that here assumed the reversed bending yield stress is 510 Newton per mm square. That is sigma y. And sigma u already available in our problem given sigma u. T max sigma is 630 megapascal. And sigma y assumed 510 Newton per mm square. So if you don't know the exact value for this yield stress, you may assume some approximate values. And then yield stress in shear for shear loading is taken as half of the yield stress in reversed bending load. So here sigma y, tau y is equal to 0.5 times of sigma y. Now calculate this shear loading value endurance limit sigma tau y is equal to 0.5 multiply with 510. So you will get 255 Newton per mm square. Let's take factor of safety. Factor of safety is equal to endurance limit. It is the ratio of endurance limit to the design stress. So endurance limit value here calculated the shear under shear load condition. Now we apply Soderberg formula. So normally the usual formula for Soderberg is equal to 1 by factor of safety mean stress upon sigma y plus variable stress upon sigma e. This is a Soderberg line for ductile materials. In this sigma m is mean stress, sigma y is yield stress, and sigma v is variable stress, and sigma e is endurance limit stress without considering any factors. But here condition is given load is torsional load. So due to the torsional load, shear stress will be induced in the object. So that's why we have calculated shear stress by using torsion formula. Now here also this equation you may be written in terms of shear stress. So factor of safety, 1 by factor of safety is equal to shear mean upon shear y. In place of sigma, shear stress will come and variable stress, and without considering the equation is 1 by factor of safety is equal to shear mean by shear y plus shear variable by shear e. But here we are considering fatigue stress concentration factor and other factors, so that sigma v multiply with factor of theoretical fatigue stress concentration factor and other stresses, other surface finish factor, K surface and K size factor. So that written like this, and substitute the values. The mean shear stress calculated 24.4, and yield stress in previous step I calculated here yield stress in shear yield stress 255. First we have calculated yield stress and then apply this relation between shear and sigma y 0.5. And here taken fatigue stress concentration factor 1, case surface finish factor and size factor. So that finally what he has asked, factor of safety. Find out factor of safety. We don't know factor of safety. So calculate the factor of safety. You will get 1.85. So one more problem we will see. This is one more model. A cantilever beam made of cold drawn carbon steel of circular cross section as shown in figure. So in this figure shown that this is a circular rod and it's a cantilever beam. One end is fixed, other end is free. The load is acting at a free end. That load varies from minus F to 3F. So minimum load to maximum load. The maximum load is 3F. The minimum is minus. Determine the maximum load that this member can withstand for an indefinite life. Using a factor of safety is 2. The given factor of safety is 2. What he has asked, determine the maximum load. So load, you don't know. So load given in terms of F, minus F to 3F. You need to calculate. The theoretical stress concentration factor is 1.42. And the notch sensitivity factor also given, 0.9. Assume the following values. The assumed values are ultimate stress is 550 megapascal, yield stress 470 megapascal, and endurance limit is 275. Size factor also given, surface factor also given. So all values are available in this problem. No need to assume. See, in given data, load given minimum to maximum. So that need to calculate mean load and mean stress. And then variable load and variable stress. Next, the bending moment, variable bending moment load and mean bending moment. And then fatigue stress concentration factor, KF. Here available only theoretical stress concentration factor. And notch sensitivity. So you know already relation between these two, theoretical stress concentration factor and fatigue stress concentration factor in terms of notch sensitivity. So I will tell the equation in next slide. So first of all, given data, write down minimum load and maximum load and factor of safety. Theoretical stress concentration factor 1.42 and this notch sensitivity 0.9 and the ultimate stress 550 megapascal. So in terms of mm square, Newton per mm square 550, and similarly sigma y yield stress and endurance limit stress, size factor and surface finish factor. So first calculate fatigue stress concentration factor. We don't know. So how do you calculate fatigue stress concentration? And relation is there. Relation between these two in terms of notch sensitivity, Kf minus 1 by Kt minus 1. So from this equation, you may write Kf minus 1 is equal to Q into Kt minus 1. So Kf is equal to fatigue stress concentration factor is equal to Q into Kt minus 1 plus 1. So this is the relation between the theoretical stress concentration factor and fatigue stress concentration factor in terms of notch sensitivity. Here, notch sensitivity value is given and theoretical stress concentration value also available. So substitute those values in this and find out the fatigue stress concentration factor. And then find the bending moment. Here, see in this given figure, the cross section is here changes from here uniform cross section to here somewhat curved. So that the more stress concentration will be occur at this point. As per stress concentration definition, so wherever the cross section varies, there more stress concentration will be occur due to the sudden changes and then any types of irregularity. So we need to calculate the bending moment. So that the maximum bending moment will be occur at point A. So find out the maximum bending moment at point A, load multiply with distance. So here that A, what is the distance? Load multiply with the maximum load multiply with the distance 125. The diameter is 13. The change in cross section diameter is 13 and previously 20. The overall length is 150. Now calculate maximum bending moment. The maximum value is 3F and 125. So 375 F in terms of F, Newton mm, the value calculated. And then similarly the minimum bending moment at point A. Here two loads are there. So that's why the bending moment also varies from minimum to maximum. So minimum load, the minimum bending moment is minimum load multiplied with distance. Same distance the load also acting minus F2 F multiplied with 125. So now calculate the mean or average bending moment. So mean or average bending moment is equal to maximum bending moment plus minimum bending moment upon 2. So what we have calculated in maximum bending moment in previous condition, so substitute here. Similarly, minimum bending moment, substitute here. And you may got this value 125F. Similarly, variable stress. Maximum bending moment minus minimum bending moment upon 2. So variable stress, same apply same values here and find out. So now you got mean bending moment is equal to 125F and variable bending moment values are 250F Newton mm. Now find out section modulus, that is Z. Z is equal to I by Y. So I is equal to 5 by 64 into D to the power of 4 divided by Y. So the distance of the cross section from its neutral axis. So that half of the cross section diameter, so D by 2. So you may written like this, 5 by 64 into D to the power of 4 into 2 by D. So here D cancel D cube, so 5 by 32 to D cube. So that the section modulus you may written directly like this, Z is equal to 5 by 32 into D cube. So now substitute to the given diameter. In our figure given the diameter is 13. So why we have taken this 13? Why not 20? So we are calculating the bending moment at A, and stresses also we are calculating at A point. Why? Because here more stress concentration will be occur due to the irregularity. And then the mean bending after calculation of Z, calculate bending stress, mean bending stress. So the mean bending stress is equal to mean bending stress value, mean bending load, bending moment by Z. So what is the mean bending moment? 125. So 125 F by 2. So here 62.5 F means to mean bending stress Newton per mm square. Similarly, variable bending load, variable bending stress. Calculate the variable bending moment is 250. So 250 variable bending stress is equal to 250 F by 2. Sorry, 250 F by Z. We also same here. Mean bending stress is equal to the Z value. This one Z. So Z value 215.15 substitute, and you so values will get 1.16 Newton mm square. So after that apply Goodman method and Soderberg line method. You know Goodman method relation between this mean stress and ultimate stress and sigma E. It is a straight line. So the mean stress available here in terms of mean bending stress. Similarly, variable stress and ultimate stress and sigma E. So you may write like this: 1 by factor of safety is equal to here mean bending moment stress. Here in previous case, you have calculated here bending moment, mean bending moment stress upon sigma U plus sigma V. Here sigma V variable stress and yes, sigma mean means variable mean bending stress, and sigma V means mean variable bending stress value. Similarly, apply Soderberg method. Soderberg method relation between the sigma E and sigma Y. So 1 by factor of safety is equal to mean stress upon variable stress plus yield stress plus variable stress upon sigma E. So while considering factors, factor of safety has already given, and other factors, if you are considering fatigue stress concentration factor, multiply with this factor. You are considering other factors, multiply. Clear? So here shown this one is Gerber method, Gerber parabola method. So by using these factors, formulas, calculate now the given diameter, calculate the given the load values. Considering the fatigue stress concentration factor, so already I told you, you may be written like this. Considering other factors, multiply with K surface finish factor and size factor. Clear? So as per Soderberg and Goodman line method. So here fatigue stress concentration factor already we have calculated. Already I told you the Kf Q is equal to Kf minus 1 by Kt minus 1. So now according to the Goodman formula, now apply Goodman theory. 1 by factor of safety is equal to mean stress upon sigma u plus sigma v variable stress upon endurance limit stress and factors, other factors. The Goodman theory according to Goodman. So this one the equation. So we have taken. Now substitute all values. Factor of safety value is given 2 and mean stress calculated 0.78 in previous condition calculated, and similarly variable stress 1.16f calculated, 1.16 variable bending stress. Now substitute those values in this equation. Surface finish factor available 0.89 and size factor 0.85. But we don't know F value in terms of the mean bending stress value and mean variable bending stress value available in terms of F only. We need to solve. You need to find F value. So in your problem, the load varies from minimum to maximum. The minimum is minus F. The maximum is 3F. So that's why we have calculated the mean load and mean stress and variable load and variable stress. And also we are using these two methods, Goodman and Soderberg. So here calculate load value, that is 57.3 Newton you got. And according to Soderberg, now apply Soderberg theory. So already you know the Soderberg formula is 1 by factor of safety is equal to mean stress upon yield stress plus variable stress and without considering any factors. If you are considering factors, again write down this equation like this: 1 by factor of safety sigma m by sigma y plus variable stress multiply with stress concentration factor by sigma e K surface finish factor multiply with K size factor. Here two factors are available. Suppose if more factors are there, so need to multiply. Like other factors, temperature factor, reliability factor, and then impact factor, so etc. So substitute those values and calculate. Here also unknown value F. So by using the Soderberg formula, once again write down 1 by factor of safety is equal to sigma m by sigma y plus sigma v by sigma e and factor of safety theoretical stress concentration factor for fatigue loading and then surface finish factor and size factor. Now substitute those values. Factor of safety value is 2 and the mean bending stress 0.58 F by 470. This is sigma v value, sigma y value, and then 1.16 is 1.16 variable stress value, fatigue stress concentration factor and surface finish factor, size factors, all values here substitute. So finally we'll get 56 newtons. Now we have calculated force value, the load value by using Goodman method and Soderberg method. So now out of these two values, find the larger one. So taking the larger of the two values, your final force or load value. So you may fix as final. So find out here. Here in first case, according to Goodman, 57.3. According to Soderberg, 56 newtons. Which one is larger? 57.3. So this one has here you can fix the final load value. So this is 57.3 newtons. So like this, you need to calculate the problems on endurance limit. Whenever the object is, the component is subjected to variable load, and also considering variable other different factors, fatigue stress concentration factor, theoretical stress concentration factor, size factor, surface finish factor, other miscellaneous factors. All these factors will affect on this endurance limit. Clear? So the endurance value is not a constant value, endurance limit stress value. It may be vary. It depends upon the type of material and the type of loading. So already we have studied in previous earlier sessions. It depends upon the type of loading. Suppose it is reversal bending load. So one factor will affect, that is a bending load factor. And axial loading, reversal axial load factor you should multiply. Shear loading factor. So all loading factor you have to take, you have to assume. Without considering these loading factors, so you may not come exact results. So that need to multiply all these values. Then only your design is safe. So I have taken references like B. Bhandari textbook of design of machine elements, and R.S. Kurmi, the machine design, and then R.L. Norton book. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.